So this is problem number 20 from the end of the chapter in the textbook. Again, if you have any questions, just pipe in at any point in time, either speak up or ask me, or type it up. So Embassy Publishing received a six-chapter manuscript for a new college textbook. The editor of the college division is familiar with the manuscript and estimated a 60% probability that the textbook will be successful. So if successful, the profit will be $750,000. So if the company decides to publish the textbook and it is unsuccessful, a loss of $250,000 will occur. So you either make a profit of 750K or a loss of 250K. So it's not a profit, but it's a loss, right? So before making the decision to accept or reject the manuscript, the editor is considering sending the manuscript out for review. A review process will either provide a favorable or an unfavorable evaluation of the manuscript. Past experience with the review process suggests that there's a 70% chance that the review will come out favorable, and there's a 30% chance that the review will come out unfavorable. So if S1 is the state of nature saying that the textbook is successful, S2 is the state of nature saying that the textbook is unsuccessful, these are the probabilities. So you're saying that if the review is favorable, there is a 75% chance that the textbook will be a success. If the review is favorable, there's a 25% chance that the textbook will be a failure. Similarly, the other way around, if the review is unfavorable, there is still a 41.7% chance that this textbook will be successful. If the review is unfavorable, there is a 58.3% chance that the textbook will still be a failure. The construct a decision tree, assuming that the first decision is whether to send it out to a review or not, and then, of course, analyze the decision tree. Now, if the review costs $5,000, what is your recommendation? So let's go through this problem. In this problem, you're first sending the manuscript out for review. The review is either going to give you a positive result or a negative result, and then after that, you are going to make a decision on whether to accept the manuscript or not to accept the manuscript. Now, this sort of multi-layered thing is what you will be doing for both the decision tree homework problems, right? They're very different kinds of problems, but the decision on whether to say, for example, in the first case problem, if I remember correctly, you are they're all you're sending out for a market research firm, and the market research firm is going to tell you whether the referendum is going to be accepted or the referendum is not going to be accepted. So the first decision is always to do that, and after that, based upon the results, you're either going to put in a bid or you're not going to put in a bid, and all of that. So that's one thing to keep in mind. And the other thing to keep in mind is that sometimes the data given to you are costs instead of profits. So if the data is cost, you're not picking the highest cost. You're always going to be picking the lowest cost. So keep that in mind. In most of the problems that we did, the data given to us was profits. So you always pick the highest value, making the most profit. But if the data is cost and you have two alternatives, you pick the lower cost and not the higher cost, obviously. Just keep that in mind. So with that said, let's solve this problem, right? So let's solve this publisher problem. Now, so the first thing that we do is first is a decision. So it's a simple decision. So I'm just gonna say this is my first decision here, and this is node 1. And here the decision is whether to there are two decisions here. The first one is the two alternatives here. The first alternative is whether to send the manuscript out to review or not. So so again, be very careful. I'm drawing a square here because this is a decision point where you'll explicitly be making a decision. Here you're saying um, uh, what you're saying here is, let me send to review. So this is the option where you send it out to review, and this is the option where you say you don't send it out to review. So no review of manuscript. So this is the option for sending it to review, and this is the option for no review. Again, when you do this on the homework and on the final exam, you can just draw this out by hand if that's easier. Right? Now, let's look at the case where you're not sending it out to review. Right? So when you're not sending it out to review, you just go with the probabilities that the editor estimated. There's a 65% probability the textbook will be successful. There is a 35% probability that the textbook will not be successful, right? So once you decide not to do a review, there is no decision left to be made. I guess there is a decision left to be made. So yeah. So I wanted to be very clear about this. So let me just change it over in case you have any questions. So even when there is no review, there is still a decision to be made. And the decision that is to be made here is whether you want to accept the manuscript or not accept the manuscript, right? So this node number 2 is whether you want to accept the manuscript or not accept the manuscript. So if you don't accept the manuscript, you don't make any money. That is always an option. Not doing anything is always an option. Just keep that in mind. So you either accept the manuscript or you don't accept the manuscript. So that's something that you can always do. If you reject the manuscript, you don't make any money. So your payoff is basically zero. Here you're looking at all profits. So zero is not the best option. If you reject the manuscript, you make $0. Now, technically, there should be no boundary for this, I guess, but you know what? It's okay. So when you write this out, you don't have to have any boundary for it. Yeah, I don't spend time on that. Okay. Now, if you do accept the manuscript, now this is when you face a state of nature. You will face the state of nature of whether the textbook is successful or not. So that's a state of nature. So I'm going to draw as much of a circle as I can, and this. So you're right. So it's a state of nature. So this is a state of nature. Here, the two options are the manuscript is successful or the manuscript is not successful. If the manuscript is successful, if the manuscript is successful, so let's say that this is the unsuccessful one, and this is the successful one. So if the manuscript is successful, you will make $750,000. The manuscript is not successful, you will make make a loss of $250,000. Manuscript is a loss, you'll make is not successful, you'll make a loss of $250,000. Right. Now, here again, there are probabilities for this. So if there is a 65-35 chance that the manuscript will be successful. So this is assuming that you don't do a review, right? So this is assuming that you don't send the manuscript out for review. There is a 65% chance that the manuscript will be successful, and there is a 35% chance the manuscript will not be successful. That is this part of the decision tree. No, this is not the homework. No. The homework is due tonight, Mike. No, for those who didn't realize that the homework is due tonight, if you already submitted the homework and you want to change your answers, that's fine. I'll just grade the very last submission that you make. So if you want to change something and submit again, please go ahead. Okay. Now, if you send this out to a review, now we face a state of nature again. The state of nature. The state of nature where the result of the review will come out. So the review result can be either favorable or unfavorable. Right? So result is either favorable or unfavorable. So remember, the 65% chance is the probability that the manuscript is successful. 35% chance is the probability that manuscript is not successful. Now here, you send the manuscript out to review. You ask a person to review the manuscript for you, and they will either say that the manuscript is good or manuscript is bad. So the result is either going to be favorable or it's going to be unfavorable. So, and there is, if I remember correctly, the probabilities for these are 70 and 30. Right? There's a 70% chance that the manuscript is favorable, and there's a 30% chance that the manuscript will be unfavorable. So this is based on past experience of the review process for the editor. He's expecting that there's a 70% chance that the manuscript, that the reviewer will tell them that the manuscript is favorable, and there's a 30% chance the reviewer will tell them that the manuscript is unfavorable. Right? So favorable and unfavorable, those are the two options. So I'm just going to copy this and paste here. Again, this is 70% chance the manuscript, the review for the manuscript will be favorable. So remember, review is different from the actual whether it does well or not. This is the best indication though, but we're saying that this is the manuscript, 70% chance that they'll say the manuscript is favorable, 30% chance that they'll say that the manuscript is unfavorable. Now, once that's done, you still have to make this part of the decision again. This whole tree will be replicated here and will be replicated here. So let's do that quickly. So this is again, you're making a decision on whether to accept or to reject the book. You can again either accept the manuscript or reject the manuscript. Remember, this is the branch where the review for the manuscript is favorable. Right? So you accept or reject. If you accept, again, you face the state of nature that of the textbook doing successfully or not. I always mess up with these arrows. So again, the favorability and unfavorability now the probabilities are different. So if the result comes out to be favorable, there's a 75% chance that the textbook will be successful. So S1 is the probability, is the event that the textbook is successful. So if the review is favorable, there's a 75% chance that the textbook will actually do well. So 75-25 probability. So these probabilities are 75% and 25%. The payoffs are the same. 700 and oops, be 750. I think I know what the problem is. So this is again 750. And 250. The loss of 250. Right. So this, let me. If you reject, you're not going to make any money. That is still $0. Now, all of this is what's going to happen if you send it out to a review and the review is favorable. So if the review is favorable, you still have to make a decision. Do I accept the manuscript or do I reject the manuscript? But the only difference is, so you'll notice that this decision tree here is replicated exactly the same as here. The payoffs are the same, 75 minus 250 and 0, 75 minus 250 and 0. But the difference is the probabilities. Before doing the review, you expect the probabilities to be 65-35, but after the review and assuming that the review is positive, the probabilities now become 75 and 25. Now, there's also possibility that the review will come out to be negative, that the person reviewing it will say that the textbook is not good enough, in which case, again, this whole decision tree will now get replicated again here. You still have to make a decision on whether to accept or to reject the textbook. If you reject, again, you don't make any money from the textbook. But if you accept, again, you face a state of nature, which is where the market, where then you have to decide whether the textbook does well or not. But now the probabilities will be different. Instead of being 65-35 without a review, or 75-25 with a favorable result, now the result for the review is unfavorable. So there's 30% chance the result is unfavorable. So now the probabilities of the textbook being successful are 41.7% and 58.3%. So the probability that the textbook will be successful is 41.7%. And the probability that the textbook will be unsuccessful is 58.3%. So the payoffs are the same still, 750. The textbook is successful. A loss of 250 if the textbook is unsuccessful. And if you reject, obviously there is no payoff. So you'll notice that this decision that you're making here, so you'll notice that this tree, and this tree are exactly the same. Accept and reject, you make a profit of 750, a loss of 250, or you make nothing based on the textbook. The only differences are the probabilities. Probabilities are based on the circumstances. In this circumstance, you're not doing a review, so you're going with your gut feeling. As a editor, you're saying, okay, there's 65% chance textbook does well, 35% chance textbook doesn't do well. Here you're doing a review, and the review is positive, then the probabilities are 75-25. If the review is negative, the probabilities are 41.7% and 58.3%. And that is your decision tree, right? Again, like I said, it'll be much easier when you draw it out by hand, but this is what the decision tree is going to look like. So let's do our calculations, right? Yes, ma'am. Let me just. All right, so let's do our calculations here. So the first calculation is when you're going through a what the hell happened here? Okay, the first calculation that the way you go about decision tree is always work backwards. So let's work backwards. Let's take this part of the decision tree, this the no review piece, and let's work backwards. There's a 65% chance that you'll make $750,000, a 35% chance that you'll lose, minus $250,000. So the expected value at node 3, so expected value at node 3 is 0.65 times 750K plus 0.35 times minus 250K, right? And this is oops. It's 0.65 times 750K plus 0.35 times minus 250K will be 400K. So 400. So that's the expected payoff of accepting the textbook with no review. So without any review, so the expected payoff here is 400K. So the decision that you have to make here is to accept the textbook or to reject the textbook. So if you accept the textbook, the payoff here is 400,000. If you reject the textbook, the payoff is $0. So obviously you will accept the textbook, right? So the decision, decision at 2 is accept. Remember, at a decision point, you will explicitly pick one of the two options. at a state of nature, you will calculate the expected value by doing that. So by accepting this decision, the expected payoff for this branch at node 2, so the expected value at node 2 will be 400,000. There are no probabilities here. There is no probability and multiply with payoff, probability multiplying with nothing that, because this is a state, not a state of nature. So the expected value here is exactly $400,000. Okay, what you have now. So that is this part of the decision tree. Now let's go to this part of the decision tree. So let's pick the favorable portion first, and then we'll do the unfavorable portion, and then calculate the expected payoff. So let's do the favorable portion. So let's begin with expected payoff at node 6. So the expected value at node 6 is 0.75 times 750,000 plus 0.25 times minus 250,000. Right? So I can just change the probabilities here. There'll be 500,000, right? So the expected payoff at node 6 is 500,000. So at node 5, decision at 5, decision at 5 is to accept because the expected payoff here is 500,000. The expected payoff here is 0. The better option between 500 and 0 is to 500. So you accept the textbook, and so the expected value at node 5. So the expected value, because you accepted the textbook, will be the value of that option, which is 500. Right? Similarly, let's calculate the expected value at node 8. So here is 40, it's 0.417 times 750,000 plus 0.538583 times minus 250,000. This payoff is wow, 167,000. So that's 167,000. Again, so this payoff is 167,000. Here the payoff is 0, so obviously it's better to do that. So again, the decision at 8 to accept the manuscript. Make sure that the numbers are all right. 150, make a loss of 250, 75, 25. Okay, and so the expected value at node 7, because you accepted the manuscript, will be, should be, okay. This is decision at 7, I'm sorry. The expected value at 7 will be 167,000. That's my payoff. Yeah. The numbers are absolutely. I just made the numbers up. It's the order of the numbers is really not that important. So the decision at 7 is to accept the manuscript. So it looks like in any case, you'll be accepting the manuscript one way or the other. Now it comes down to whether you want to send it to a review or not. So let's calculate that. So there's a 70% chance. So let's see. So now we have to calculate the expected value at node 4. For node 3 and 5, the decision is to accept the manuscript. Node 3, right? At node 3, there is no decision. So node 3, you're calculating the expected value because node 3 is a state of nature. So this is what you face after you decide to accept the manuscript. So after you decide to accept the manuscript, either the textbook will be successful or the textbook will not be successful. You don't know which one is going to happen here. So there is no decision here. So only when you have a square box, you have a decision. With the circle, with the state of nature, there is no decision. This is not under your control. So you're just calculating the expected payoff here by multiplying probability with payoff, probability with payoff. And this is what gives you the 400,000. So here you're explicitly making the decision to accept and not to reject the manuscript. Because that's the case, the decision here is accept and there is no decision here. This is just a state of nature. It's what happens after you accept the manuscript. People either like the textbook or they don't. It's really not something that you can control. So the expected value at node 4, because this is again a state of nature, the expected value at node 4 will be 0.7 times payoff here. So we know that the payoff at node 5 is 500,000. And there's a 30% chance that the review will be negative, in which case you the expected payoff is 167,000. So now it'll be 0.7 times 500 plus 0.3 times 167. This $400,100. Yeah, that doesn't look right. Yeah, the 400,000. So that is the expected value here. So the decision at node 1 to send to review. Why is the decision to send to review? Because if you send it to review, you get a payoff of $400,100. If you don't send it to a review, you get a payoff of $400,000. So this branch has a payoff of $400,000, and this branch has a payoff of $400,100. So you expect to make more money. Now, why do you expect to make more money here? Because you're more likely to know what's going to happen. So here we are just writing that, 75%, 25%, you make 750, lose 250, but it's always better to have more data. So because you have better data, you'll end up with a slightly higher expected value. So the difference between these two options, here the expected payoff is $400,100. Here the expected payoff is $400,000. So the difference between these two is only $100, not much. So if you look at the next part of the question, it says, if the review costs $500,000, what is your $5,000? What is your recommendation? So if the review itself is going to cost you $5,000, then the expected payoff here is not $400,100 anymore. You have to subtract $5,000 from that. So if the review costs money, then it will actually be $395,100, in which case it makes sense for you not to send it out to review. Now, in any case, whether the review is favorable or unfavorable, or you don't send it out to review, in any of these cases, you'll always be accepting the textbook. So none of these options tell you to reject the textbook. So what is the final decision? The final decision here is to send the textbook out to review, and whatever the result of the review, you still accept the manuscript, accept the textbook. I don't know why. That's the decision here. Now, it might have been that, so let's say that the payoff, instead of being 750 minus 250, 750 minus 250, the payoffs were different. Or let's say that the probabilities here being 417 and 583, let's say that the probabilities were different. Let's say the probabilities were flipped, right? Instead of being 75-25 here, let's say the probabilities were 75-25 the other way. So if the probability was 25, if the probabilities were 25 and 75 here, then the payoff here would have been, and obviously 75, okay. They have been zero, basically, right? They have been $0. The payoff here would have been $0, in which case accepting or rejecting would have been the same outcome. And if it was higher, let's say this was 80-20, then it would make sense for you to actually reject the manuscript. So the probabilities here make a huge difference, and so do the payoffs. Right now it's going to be 417. And 583. Yeah. So the decision here will be always to accept the manuscript, but it is better to send it out to the review. Send it out to a review, because the review will give you a better idea of whether it's going to be a favorable acceptance or not. That's the bottom line. So that was problem number 20. Again, I will post that solution up on Canvas. Let's see if I can do problem number 21. So I'll try to do some part of problem number 21. But you know what? Let's try problem number 24. Try problem number 24 and see how this works out. So I will do some part of problem number 24, maybe till I will draw the decision tree, the calculations themselves. Or you know what, I'm just going to go. So what I'll do is I'm going to solve problem number 20. What should I call it? I will solve problem number 24 here. Now, if the class lasts longer than 9:20, you guys can leave. I'm just going to finish up the class. The rest of it will be in the video. You can watch the video after you've done with whatever else you need to do. But my plan is to solve problem number 24. So let's do problem number 24. So, it was problem 19, right? Yes, that was problem. No, problem 20. I'm sorry. So I'll change that to problem 20. So we'll be doing problem number 24 now. Now, one of the reasons I wanted to do that is that it uses some of the Bayes theorem stuff. So I just wanted to go through a problem that actually uses some of the Bayes theorems. Right. To save on expenses, Rana and Jerry agreed to form a carpool for traveling to and from work. Rana preferred to use the somewhat longer but more consistent Queen City Avenue, while Jerry preferred the quicker expressway. He agreed with Rana that they should take the Queen City Avenue if expressway has a traffic jam. And the payoff table is given here. Now here the payoffs are time. So you're saying that if they take Queen City Avenue and the expressway is not jammed, it'll take them 30 minutes. And if the expressway is jammed, it'll still take them 30 minutes because obviously they're not traveling on the expressway. So it's 30 minutes to go by Queen City Avenue one way or the other. But if the expressway is open, the expressway they'll reach work in 25 minutes. If the expressway is jammed, it will take them 45 minutes. And based on experience with traffic problems, they expect the expressway to be jammed 15% of the time. There's a 15% probability that expressway is jammed. So in addition, they agreed that weather seemed to affect the traffic conditions. So it can be either clear, overcast, or it can be raining. So if it is clear, so the traffic is jammed 80% of the time when it's clear, 10% of the time. The traffic is not jammed. If the probability that it will be clear given that the traffic is jammed is 80%, probability that it will be overcast given that the traffic is jammed, it's 20%. So if the traffic is jammed, it's not jammed. Sorry, traffic is not jammed. 80% of the time it's clear, 20% of the time it's overcast. If the traffic is in fact jammed, then there's a 10% chance of clear skies, 30% chance of overcast skies, but it's a 60% chance of rain. So when there is no rain, basically it doesn't look like the expressway is jammed. Anyway, using the Bayes theorem of probability revision to compute probabilities for each weather condition and for whether the expressway is open or jammed. So you want those probabilities and show the decision tree for this problem. What is the optimal decision strategy? So let's draw the decision trees and we can calculate the probabilities based upon that. So remember, so what is the probability of C given S1? So this is a conditional probability. So again, remember from your statistics classes and other classes where you might have used this, this is the probability that the skies will be clear given that you notice that the expressway was not jammed. So whenever you notice that the expressway was not jammed, there's an 80% chance of clear skies. There is a 20% chance that the sky will be overcast, but not raining. But whenever you notice that the expressway was jammed, there is a 60% chance that it was raining, 30% chance that the skies were overcast, and 10% chance that the skies were clear, right? It's probably because of accidents and whatnot. But anyway, so these are the probabilities that you noticed. But the probabilities that you need are not probability of clear skies given that there was no jam on the expressway. It is the other way around. What is the probability that there will be a jam? There will be no jam on the expressway given that the skies were clear. So you have to calculate probability of S1 given C. Because look at all, so it's always S1 given E or S1 given L or S1 given H. So you're always calculating the probability of the state of nature itself conditioned on other factors. But this is given to you the other way around, so you have to do those calculations. And we will do those calculations right now. That's what we're doing in this problem. Okay, so if you remember correctly, we were doing this using some of the tables that we had. So let's do this with the table. So let's calculate the probabilities first, and then we can draw the decision tree. Right. So what I'm trying to show you is this. If you remember correctly. Right. So these are the, this is the table that you should construct, where the first column, you always say those are your states of nature here. So always start with states of nature. So instead of calling them S1, S2, I will actually say that clear expressway. This is S1. And you have jammed expressway. This is S2. These are your two states of nature. Expressway is clear or expressway is jammed. You don't know which one is going to happen. That's really not under your control, right? So those are your two states of nature. Then you start with prior probabilities, have the conditional probabilities, and then you calculate the joint and posterior probabilities, right? So let's calculate that. So start with prior probabilities. Prior probabilities are what were your original estimates of the probability. So if you remember correctly, they estimated the right. So they estimated there's a 15% probability that expressway is jammed. So their prior estimation of probabilities is that there's a 15% chance that expressway will be jammed. I'm sorry, it's 15% chance. There's a 85% chance that expressway will not be jammed, right? And then we had conditional probabilities. So what are these conditional probabilities? So this is the probability that given that the expressway is jammed, what is the probability that the skies are clear? What is the probability that the skies are not clear, and so on? So if you remember. So these are the probabilities that we had before. So again, you can put them down in a table like this. It just makes your life so much easier. So here, let me actually. So here we're trying to calculate skies are clear. This is a table for skies being clear. That's C. So what is the probability that the skies are clear whenever the expressway is jammed? We know those probabilities. Those were given to us. Ah, damn. 80% and 10%. So these are the probabilities. So So whenever you saw that there were no jam, the skies were clear. The probability that the skies were clear is 80%. Whenever you saw that there was a jam, the probability that the skies are clear is 10%. So it's 80% and 10%. These were your conditional probabilities. Using that, you can calculate the joint probabilities. So joint probability is just prior probability times the conditional probability. And if you add these joint probabilities up, this will give you the probabilities that the skies are clear. So I think that's called the marginal probability. So about 69.5% of all of their drives, they noticed that the skies were clear. Now you can calculate posterior probabilities. And that will be the joint probability divided by the marginal. So What is this probability? So again, I just want to show 4 decimal places. So let me. So 97.86% and 2.16%. What are these probabilities? What are they representing? So remember that this probability, the 80% probability. So this is the probability of C given S1. That's the probability, the 80% probability. So this was 80%. So what was this probability? You're saying that you noticed that there was no jam on the expressway. So when you notice that there was no jam on the expressway, the probability that the sky was clear was 80%. So 80% of the time, whenever there was no jam on the expressway, you notice that the skies were clear. That is this probability. But what is this probability here? So this is the probability of S1 given C. So this is the probability that you notice that the skies were clear. So whenever the skies were clear, what is the probability that there was no jam on the expressway? And that probability is 97.8%. Right? And that is the difference. So in this case, the event that you noticed was that there was no jam on the expressway. Then the probability of the sky being clear is 80%. So it's a if there was no jam on the expressway, there is an 80% chance that the sky will be clear, 20% chance that the sky was overcast. This probability is saying that whenever I notice that the skies were clear, there is a 97.84% chance that there will be no jam on the expressway. There's almost no chance of a jam on the expressway whenever the skies are clear. There is a small probability that there is still a jam on the expressway. There's a probability that there is a jam on the expressway given that the skies are clear. And this probability is 0.0216, probably because of accidents and whatnot. That is this probability. Okay. Now, similarly, so it comes down to which event did you notice first, right? That is what conditional probability is, conditioned on the fact that this event has already happened. Did you first notice that the skies were clear, or did you notice that there was no jam? So if you notice that the skies were clear, and then you're trying to calculate the probability of jam versus no jam, these are the probabilities. But if you notice that there was no jam, and you're trying to look up what the weather condition was, there's an 80% chance of clear skies, 20% chance of unclear, non-clear, of overcast skies. So this probability is here. Let me just. So we calculated this for skies being clear. Now let's calculate this for overcast conditions. For overcast conditions, the 20% and 30%. So when you notice that there was no jam, there is a 20% chance that the skies are overcast. Similarly, when you notice that there was a jam, there's a 30% chance that the skies are overcast. So it's 20 and 30 here. Now the prior probabilities are the same. Skies being clear, expressway being clear, expressway being jammed. These prior probabilities remain the same. But now we have these conditional probabilities. So again, this is the probability that the sky was overcast, given that you first noticed that the highway was not jammed. That probability was 20%. Using that, we calculated the probability for the other way around, which is probability that the expressway is not jammed given that the skies were overcast. That probability was 79.07. So if you first notice that if you notice that the skies were overcast, then there's a 79.07% chance, about 79% chance that, you know what, let's just use 2 decimals. It's so much easier. Now 4 is okay. Let's do 4. Let's do 4. I don't know why I'm dithering on something so simple. But probability that the skies were, that there was a jam on the expressway when given that the weather conditions were overcast, that probability is 0.2093, right? That's this probability. Similarly, I can calculate the probabilities for, we did overcast and clear skies. Let's do rain. Happens when there was rain. When there was rain, you'll notice that there was no chance of a roadway being clear at all, right? So this probability was 0 and 60, 0. Here the posterior probabilities are pretty clear. So what does this mean? So let's look at these probabilities. So let's look at this one here for this time. What is the probability that you notice rain when you first notice that the skies were roadway was not jammed? You never noticed that. The probability that there was rain when you noticed that the sky that the roadway was jammed, expressway was jammed, that was 60%. Now, what are these probabilities that we calculated? So, what is the probability that the roadway will be jammed, will not be jammed when there is rain? This probability is 0%. What is the probability that the roadway will be jammed given that there is rain? This probability is 100%. So 0% and 100%. So if it rains, then the expressway will definitely be jammed. There is no chance that the expressway will not be jammed. And that's what you have. Okay. So these are the probabilities that, this is how you calculate probabilities based on Bayes' theorem. Again, I will post these calculations on Canvas. But let's draw the decision tree here, right? So so the decision here is whether to take the expressway or not to take the expressway. And there are no multiple decisions here. There is just a single decision. So let's say, so whether you take, you agree that they should take Queen City Avenue if the expressway has a traffic jam, but you don't know whether the expressway is going to have a jam or not, because that's a state of nature. That's the following payoff table. But one thing that you can notice is that it seems clear, overcast, or there is rain. So that is something that you can notice, right? So this we'll begin here with the state of nature. So you get out of the house, and the first thing you notice is a state of nature. This state of nature is, just going to call this 1. There are 3 options to this state of nature, and these 3 options are: skies are clear, skies are overcast, and it's raining. So these are the 3 options. Again, this is not under your control. Skies being clear, overcast, or raining. So those are 3 options. Let me Get out of the house, and this is the first thing that you notice. Skies are either clear, overcast, or it is raining. Now, in all of these three cases, you still have to make a decision. So the decision that you have to make is whether to take the expressway or not to take the expressway. So I'm just going to call them D1 and D2. So we know that D1 is taking Queen City Avenue and D2 is taking the expressway. You know what, let me just. This is the option of Queen City Avenue, call it QCA. And this is option of taking the expressway. And call it expressway. Right. Now, once you make this decision, you again face a state of nature. And this state of nature is whether the thing is packed, jammed, or not. So this is the state of nature where expressway is jammed or expressway is not jammed. Again, this is not under your control. You won't know that till you get there to the expressway. So you still have to make a decision before you take the expressway. So the expressway is jammed or expressway is not jammed. So I'm going to call it open, jammed. Right. So if the expressway is open, then if you take Queen City Avenue, it's going to take you 30 minutes one way or the other. Expressway is jammed. Take you 30 minutes. Because this is the option of taking Queen City Avenue. Expressway being jammed or not jammed really doesn't make sense. Oh, you know what? I guess we don't need to do that. So let me just change this to expressway. So this is the option of taking the expressway, and this is the option of taking Queen City Avenue. Take Queen City Avenue, you don't have to face any state of nature here, because one way or the other, it just takes you 30 minutes. Otherwise, here it takes you 25 minutes and 45 minutes. So you come outside the house, you notice that the skies are clear. Now you have to make a decision. Do I take the expressway or do I take Queen City Avenue? If you take the expressway, the expressway will either be open or it'll be jammed. This is not under your control. These are probabilities, which we'll put down in a second. But if the expressway is open, it'll take you 25 minutes to reach there. If the expressway is jammed, it's going to take you 45 minutes to reach there. Or you could have chosen the option of taking Queen City Avenue, in which case it will take you 30 minutes to get there. Now, what is the probability of open and jammed given that the skies are clear? Now, these are the probabilities that we just calculated. So given that the skies are clear, what is the probability that the expressway will be open? And what is the probability that the expressway will be closed? So that is 97.84% and 2.16%. Before I proceed. All right, so officially it's 9:20. The class time is done. I'm going to finish, like I said, I'm going to finish with this problem and post this video on Canvas in a few hours once they're done encoding this. But you're not required to stay. If you want to leave, you can go ahead and leave. But I will be solving the problem here. Right. So the probabilities are 97.84% and 2.16%. So let's put that down here. Right? Now, there are no probabilities to worry about here, but this decision tree will be replicated here and will be replicated here. The only difference being these probabilities, right? So again, because whether it's overcast or clear or whatever, you still have to make a decision on how to get to the office. But I guess they have to make a decision on how to get to the office. So this is taking the expressway. This is taking Queen City Avenue. Right. If they take Queen City Avenue again, it'll take them 30 minutes to get there. They don't, then they still face a state of nature. They took the expressway could be open or closed. Open. Now the probabilities are obviously not going to be 978 and 2.16. Those probabilities are going to change. We'll put them down right now, but the payoffs are the same. It'll take you 25 minutes. If the expressway is open to get to the office, it'll take you 45 minutes otherwise. Now, this is one example where the payoffs are times, and the lower the time, the better it is for you. So here, whenever you're making a decision, you won't pick the higher value, you'll pick the lower value. So, but what are the probabilities now? This is the probabilities of being overcast. So based on being overcast, the probabilities are 79.07% and 20.93%. So 79072093. There you go. And similarly, if it's raining, still have to make the same decision. Right. Let me change the numbers. It can't be the same. 3, then 4, 5 here. Again, the numbers really, the order in which you write the numbers really don't matter. 6 here. So this is the Queen City Avenue option again. You take Queen City Avenue, it's going to take you 30 minutes, one way or the other. It's not gonna matter. So it's 30 minutes. But if you take the expressway, you again face a state of nature of expressway being open or jammed. And then you have to face the state of nature. Now again, the probabilities will be different here. In fact, probabilities are pretty stark, if I remember correctly. The payoffs are all the same. Now, when it's raining, you know that there is no chance that the expressway will be open. So this is 0. And when it's raining, you know that the expressway will be jammed 100% of the time. So this probability is 1 and 0. So this is the decision tree. Now, the interesting thing about this decision tree is that the first thing that you face is not a decision, but in fact a state of nature based upon the weather outside. So you first look at this state of nature and then you make a decision on what you want to do. So let's do the calculations for this decision. Right. So let's begin. Let's begin here. So let's calculate the expected payoff. So the expected value at node 3 will be 0.978 times 0.25 minutes plus 0.216 times 45 minutes. So that is 25.42 minutes. So it's 0.978 times 25 minutes and wait, is that right? Right. 25.42 minutes. For 2 minutes. So here there are two options. So at decision point 2, the decision at node 2 is, if you take the expressway, it's going to take you 25.42 minutes. If you take Queen City Avenue, it's going to take you 30 minutes. This number is lower than this number. The average, the expected time is lower than this number because this is 25.42 and this is 30. So you pick the lower number. So here you take the expressway. That's the decision because it takes you lower, right? And so the payoff, so the expected value at node 2 is 25.42 minutes. Okay? That's that. Next, let's calculate the expected payoff at node 5. Expected payoff at node 5 is 0.7907 times 25 minutes plus 0.2093 times 45 minutes, which is 907. That's about 29.186 minutes. So decision at node 4. So the payoff here is 29.18 minutes over 29.19 minutes, I guess. Just 9.19 minutes. So if you take the expressway, on an average, it's going to take you 29.19 minutes. If you take Queen City Avenue, on an average, it's going to take you 30 minutes. So it is better for you to take the expressway than to Queen City Avenue. So again, so decision at node 4 is to take the expressway. And so the expected value at node 4 will be 29.19 minutes. And finally, what's the decision at node 6? At node 5? Sorry, what's the expected value at node 5? So node 5, because it's raining, there is no chance that the expressway will be open. It's going to take you 45 minutes. So the expected value here is 0 times 25 plus 1 times 45, which will be 45 minutes. So the decision at node 6 is 7. I'm so sorry. The decision at node 6 is, so if you take the expressway, it's going to take you 45 minutes. If you take Queen City Avenue, it's going to take you 30 minutes. So here it is take Queen City Avenue. The expected payoff at node 6 will be 30 minutes because you chose to take Queen City Avenue. Right? So what's the decision? The decision is, if the skies are clear or overcast, then take the expressway. If it's raining, take Queen City Avenue. If the skies are clear, it's going to take you 25.42 minutes to get to the office. On an average, if it's overcast, it's going to take you about 29.19 minutes to get to the office. But if it's raining, you should take Queen City Avenue, in which case it'll take you 30 minutes to get to the office. You can also calculate